Hello everyone, my name is Emre. Today I'm going to present our data science project entitled Breast Cancer Diagnosis via Machine Learning. So let's get started. So our outlines are going to be as follows. I'll first give a brief introduction about the problem and how we approach to solve this problem. Secondly, we'll explore the dataset that I utilized. And next, we will see the feature importance and selection procedure that I applied during feature selection. And then we will see the model development process, what kind of machine learning models I used and how I selected their parameters. And then we will see the training and evaluation results. And afterwards, we will see the model deployment stage. And at the end we will conclude with this brief discussion. So breast cancer is one of the most frequent cancer in females. It affects about 1 in 8 women, so it's a big problem still. So not all breast lesions are malignant, some of them are benign, so they need to be detected beforehand. So there are different ways of screening and diagnosing these breast cancer cells. One way is physical examination, other way is mammography, third one is fine needle aspiration cytology, fourth one is core needle biopsy, fifth one is digital breast tomosynthesis, sixth one is ultrasound, and the last one is magnetic resonance. So in this work, we will focus on the fine needle aspiration FNA cytology method because our data set is based on that kind of examination. So breast cancer can be accurately predicted and diagnosed using machine learning techniques. So today we are going to explore how it's being done. So dataset exploration. So on the right hand side of the page, we can see a malignant image of a malignant. We can see a magnified image of a malignant breast FNA. And the visible cell nuclei have been outlined with the help of a curve fitting program here. So basically, in the dataset, there are some handcrafted features extracted from these nucleus, and we'll see those in a bit. So a fine needle aspirate dataset is used to develop breast cancer diagnosis model in this work. And the dataset is presented in a CSV file with 32 columns and 569 rows, where each column corresponds to a handcrafted feature and each row is a sample. Original images, like these images are not accessible. I'm guessing it might be because of the privacy concerns, because in the dataset file there are also like patient IDs. So probably using those patient IDs, you can track back like who those patients are. So they didn't share the like image dataset. They only shared the like handcrafted features in a CSV file. And 10 real-valued features are computed for each cell nucleus, as you can see in this image. And the mean, standard error, and worst or the largest of these features were computed for each image. So 10 times 3 features, it makes like 30 features in total we have. So the data set looks like this, basically. So it's a binary classification problem because there are two classes, benign and malignant samples. So in total, there are 357 benign samples and 212 malignant samples. So the first column, as we can see here, is the ID, patient ID. And the second column is the diagnosis. So these are going to be our labels. So M stands for malignant and B stands for benign samples. So there are in total 32 columns. 2 of them are for ID and diagnosis, and the rest of them are for the features. So the first thing that we apply during the usage of the data is to first clean out the dataset. So in the original data file, there were 33 columns, and the last column was consisting of all NaN values, which stands for not a number. So we discarded all of those columns, like the last column. And next thing we want to do is to apply feature importance and selection procedure. So although there are like 30 features in total, since we are planning to deploy this model, asking users to like enter 30 scalar values is a bit tiring procedure. So to keep things a bit simpler, we select a subset of those 30 features. So I selected five features out of these 30 features. So I want to decide like which features are the most important features for this dataset. So there are different number of techniques that you can use to kind of do the feature selection stage. One of them might be using maybe minimum redundancy and maximum relevancy based techniques. Others might be model based, like which tries to maximize the classification performance of the model by iteratively dropping or adding more and more features. But that would be kind of model dependent. So I want to use something a bit more model agnostic. That's why I want to kind of see which features kind of contribute to the classification the most. So here what we do basically, so we train the models multiple times, and in each training we are discarding a feature. For example, let's say in total we have normally 30 features, but in each iteration we are discarding one feature, and in this way we are left with 29 features, and we are observing the change in the accuracy. If there's a negative change, it means that that feature is important feature, so discarding it would harm the performance of the model. So applying this technique, we find five most important features and noted them here. So next thing is the model development stage. So I tried four different machine learning models. The first one is support vector machines. SVMs are one of the most robust prediction methods, and they map the training examples to points in space so as to maximize the width of the gap between two categories. The objective of SVM algorithm is to basically find a hyperplane in an n-dimensional space. So as we can see here, like these hyperplanes on each side of the decision boundary. So basically it tries to find a plane that has the maximum margin between data points of both classes as depicted in this figure. So basically it tries to maximize the distance between these two hyperplanes. And it does this by using something called support vectors. And these support vectors are just the data points which are closer to the hyperplane, and they can greatly influence the position or orientation of the hyperplanes. So the next model I used is the random forest. Basically, random forest consists of many individual decision trees which operate as an ensemble, and each individual tree in the random forest spits out a class prediction, and the class with the most votes becomes the model's prediction, as shown in this figure. For example, in this figure there are predictions of 1 for 6 times and predictions of 0 for 3 times. It means that the majority is the majority of the decision trees are predicting 1, so the result is going to be 1. So the fundamental concept is basically like wisdom of crowds, and there are three main hyperparameters in the random forest. There's node size, number of trees, and number of features sampled. So the next model I use is the k nearest neighbors, and in KNN, class label is assigned based on a majority vote. and the distance between the query point and the other data points are used to determine which data points are the closest. Euclidean distance is the most commonly used distance measure, although there are some other distance metrics like Manhattan distance or some other distances. The k-value in the Kenan algorithm defines how many neighbors will be checked to determine the classification of a specific query point. For example, if the k is equal to 3, then it means that it's gonna check with the 3 closest points and choose the most voted class. So the lower values of can have high variance but low bias, and larger values of k may lead to a higher bias and lower variance. So there's kind of a trade-off. It's a parameter that needs to be optimized. So the last model I tried is the multi-layer perceptron (MLP). So a perceptron is a single neuron model basically, and the building blocks of neural networks are these artificial neurons. Simple computational unit. They are basically simple computational units that have weighted input signals and produce an output using an activation function. Activation function is basically it's a mapping function which kind of takes inputs and maps it to some nonlinear output. And a row of neurons is called a layer, and one network can have multiple layers. It must have at least one input and one output layer, as shown in this image. These blue neurons they belong to input layer, and this green neuron is the output layer. And there are some hidden layers in the middle. And these W's stands for weights. This V is the weights for the hidden layer. So model training and evaluation. So we kind of tried different machine learning models, as we mentioned, and we can see that KNN is the best performing one amongst others. Since our dataset is a bit unbalanced because there are more malignant samples than benign ones. Sorry, there are more benign samples than the malignant ones. We had to check other performance metrics like precision recall and F1 score, not only the accuracy. But we can see that KNN has the best accuracy, also the best F1 score and recall and precision metrics than other networks. MLP is kind of performing a little bit better in precision of benign samples and recall of the malignant samples, but it's only 1% difference. But when we go to check the precision of the malignant samples, when it's 91% in KNN, it's only 87% is in MLP, so it's a huge difference. So that's why I chose KNN as my deployment model, and I optimized its hyperparameters like the K value or the leaf size using a grid search method, which is mentioned in my report. So the last stage is the deployment of the model. So I chose Microsoft's Azure cloud platform as my deployment website because it was easy to use and it gives you a free hosting service. So basically I created an HTML file where we take 5 different inputs from the user, and when we submit those values, it gives us an output predicting whether the patient is diagnosed benign or malignant, and it also shows the confidence value in percentage. So the source code of my project is available in this link, and the dataset can be found in the same GitHub repository. There's a file name called breast cancer data with like 5 features. And my applications website is this. If you want to try it, you can just go to the website and give it a try. Opening of the website takes a bit time, like 1 to 2 minutes. I'm not sure why this is happening right now, but I'm guessing it might be because of the like Azure's hosting speed. Sometimes it works very smoothly, but sometimes it works a bit slower than other websites. So if you want to try, you can go ahead. So discussion. So in this work, we tried different ML models, and we see that ML models can provide sufficient performance to classify breast FNA samples for whether they are being benign or malignant. And I think for the deployment stage, inputting scalar values is not a very intuitive way of deploying such models, because users might not know those kind of handcrafted features, and they cannot compute them by themselves. So I think this model could have been deployed in a way that users could upload their own breast FNA images, uh, so that they don't have to deal with those handcrafted features. I mean, the model should be able to just take the images and then give the output. But the thing is, we don't have access to the original image files, so we had to use this scalar valued model. So thank you for listening. Here are my references. You can reach out to me if you have any questions. Thank you.